Okay, ladies, so hopefully you've watched What is Current and you've read 22.1. And so I'm going to summarize what I'd usually do in class, and we'll see if this goes too long. But the idea of a circuit is that it's just a closed loop. So electrons can go around the loop. It's like an obstacle course for electrons where we can make them do something useful so that their potential energy is transformed into some other kind of energy. So I want sound energy instead, or I want my light to come on. So I'm just transforming electrical energy into some other form because electrons are very versatile and they can do a lot of different things for us. So I did want to mention though too that in the video when he talked about flow of charge in a closed loop, we don't always get flow of charge. Like here's my 9-volt battery, and so if I put, I've got the negative side and the positive side here. So if I put my finger across the two terminals, I am not going to get a flow even though there's a closed loop. And why is that? So let's talk about that in a second here. So the reason that is because there's too much resistance in my skin. So the resistance is referred to as R in this equation for Ohm's law. And in this case, we don't have very much current flow at all because my skin is resisting that current flow. This is a 9-volt battery, like I said, but because I have so much resistance in my skin, that I just don't get much current flow. And current is represented by the variable I. So that is the dependent variable in this situation. Voltage is all set by the battery or whatever the outlet would be. That is an independent variable, and then resistance is set by the physical characteristics of what's between the two terminals here. So it would be different. Like I said, you're not supposed to put this on your tongue because the resistance of wet things is less. If we put a wire between here or a light bulb, then obviously that will be less resistance and we'll get current. So on here we have our two independent variables, and then current is the dependent one in this relationship. I have this visual to show the linear and inverse relationships here. So let me just switch to that. So here you can see like they have the equation written differently, but if I increase the number of batteries, then current goes up, and that's represented by the size of the letter. I reduce the number of batteries, current should go down. Those two have a linear relationship. Let me put it back where it was. And then if I change resistance, that's kind of represented by these black dots in here, and like they're how the stuff in here doesn't let current go through very easily. So if I make that bigger, then current won't go through as easily. Current will go down. Reduce resistance, just like it sounds, then more current should flow. That should make sense that these have an inverse relationship to each other. Okay. Sorry. Switch back. So then once we get to the math, I like this equation the best because it shows like the independent variable on the left hand side, but it does, some people like this visual to help them do the algebra, because you will do problems where it asks you to solve for voltage or resistance because you know the other two variables. So if you like that, I'll be posting this PowerPoint and you could copy that down. Units for resistance you saw in the book. And then I just wanted to mention that Ohm's law, like Newton's laws, we've never seen broken. But Ohm's law isn't really a law that can't be broken. This one really is a rule of thumb, because for some objects, they don't really follow a linear relationship between voltage and current all the time. So they sort of bend the rules, and the curve, when you look at it on a graph, the current doesn't go in a linear relationship. So, okay. And then a couple more vocab items here. So there are these items called resistors, and that's referring to a specific electrical thing. They're pretty small. This is really zoomed in. Here's what it looks like in real life. Like these are hanging off of like some bowl. And they are designed to follow Ohm's law to be really predictable and control current so that current never gets too high. When we take, I hope we'll get a chance to take some appliances apart, and you might get to see some on the inside. And then another thing that's important to know is how about the resistance in wires? I mean, wires are supposed to have really small resistance. It's kind of their job, but they're not infinitely small resistance. And so when we think about the resistance of a wire, the best way to make a low resistance wire would be to make it short. So here I'm looking at length here. Short, fat, cold, and then copper is what we tend to make it out of. Silver would be even better, but that's really rare and expensive. So what we tend to think about is Santa is really low in resistance. He really gives in easily, and he gives you presents, even maybe if you haven't been perfectly good. So that's one way to remember that resistance is low when the wire is short, fat, and cold, because Santa is, I guess, he comes from the North Pole, so that's what I think of. Okay, and then the material matters too. That part doesn't really go with Santa. But conductors are great, and a lot of what our wiring in the United States is in copper. Okay? All right, we're going to stop there for today. I think that's enough content. And so look over your notes or look over the section again, and then you'll be ready to do the reading check over 22-1.